Let's talk now about two different random processes and their cross correlation function, which by definition is this. XY means two different processes at two different times, a T1 and a T2. By definition, it means the X at T1 and the Y at T2, because I put XY here. It's going to turn out that the order matters. If both are wide-sense stationary, this guy is just a function of the time difference between T1 and T2. If you do a little variable substitution, take the same guy and put in a negative argument, find that it's the same as the cross correlation of YX. So that RXY is not quite RYX. They're minus of each other, or minus the argument of each other. Yeah, so YX of minus T is XY and tau. It's tau minus tau. Anyway, order now matters. It didn't with the autocorrelation function. An example, say Y is just a delayed version of X, where the delay is capital T. Well, the mean of Y is just the mean of X. Because X is wide-sense stationary, that's just a constant, whatever X's mean is. For this cross correlation, it meant this by definition that, and Y at T plus tau is X at T plus tau minus T. If you look at what that means, it's the autocorrelation function of X at tau minus T. So it turns out the autocorrelation function, or this cross correlation function, XY, is just a delayed version of X's autocorrelation. If this were what Rx of what, if this is what the autocorrelation function of X looked like, this might be what the cross correlation XY would look like. Some delayed version, in this case, capital T equals a half. So it's just the same thing shifted to the right. Here's a little property. If two processes are independent and wide-sense stationary, their cross-correlation function is just the product of their means. You can do this. It's a very simple proof. Here's what it means by definition. Since they're independent, that expectation breaks up into a product. And since they're wide-sense stationary, each of these guys is just their means. I guess I'll try to get this done in this video. There's a bunch of properties for stationary processes, or certainly wide-sense stationary processes. One is symmetry. I guess I won't go through all the proofs. What is its symmetry? Because the argument could be minus tau, it's the same as tau. This is for the autocorrelation function. It means the autocorrelation function is an even function of tau. The mean square value, this is kind of obvious. The mean square value is just the autocorrelation function evaluated at 0. The square root of that would be the root mean square, or RMS, of the random process. Linear combinations. Any linear combination of wide-sense stationary random processes is also wide-sense stationary. Take a Z equals AX plus BY. X and Y are both wide-sense stationary. And Z is also wide-sense stationary. And its autocorrelation function will look like this. I'm not going to go through this proof. This is for Z is just a function of two random processes, but by induction, any linear combination of more variables, more processes. The autocorrelation function is also the same linear combination, not the same linear combination. It's a linear combination. Got to do the cross. Property 4. If a function is periodic with period capital T, here's what that means. Here's what a periodic function means. F in a T with an argument T plus capital T is the same as F at the argument T. It has a period capital T. Well, if the random process is periodic, and that means this. The random process, the argument T plus capital T is the same as the random process T. What does that mean for the autocorrelation function? This, and it means the autocorrelation function is also periodic. So if a stationary random process is periodic with period T, then its autocorrelation function will also be periodic with period T. So then if any component is periodic, in a component meaning it's a sum of things, then its autocorrelation function will also have a periodic. Here's one. I just stated this before, but if the limit of the autocorrelation, if the limit goes to 0 as tau goes to infinity, then the mean of that process is 0. Inverse is not necessarily true. If there is no periodic component in that random process, then that limit goes to the square of the mean. So just without knowing anything else, if you know the mean is 0, it does not mean this limit goes to 0. This limit might not even exist. But this direction of logic does work. If this limit goes to 0, then the mean of the process is 0. Here was an example of a periodic process. Let's say y is just this random variable x, which is drawn from a normal distribution. Then the mean, normal with 0 mean, then the mean of that process y is just the mean of x, which is 0. Autocorrelation function, if you go through, it's the variance of x. It is not 0. So the mean was 0, but this limit was not 0. That's what I mean. The converse doesn't necessarily hold. And that's because this was a periodic process, in fact, constant. If it were some other periodic process, but not a constant, I think the limit wouldn't even exist. It would be like a sinusoid. I'm not going to go through this proof again, but the maximum value of an autocorrelation function is where the argument is 0. The autocorrelation function is maximum at tau equals 0. Here's a kind of a simple proof. If you want to look through it, I'll just pause this screen, pause the video here. I think I'll stop. I just stated what a whole bunch of very good properties of wide-sense stationary processes. You might go back to those and use them.